Assalamualaikum to Miss Nur Saada binti Zainal. I am Luqman Hakim bin Mahmud Zuhdi, matric number CD180201, and I am from Group 2, from Section 3 and 4. So our group will present about M2, lab report M2, which is torsion test. Okay, firstly our members is Ladin, Ipan Bakri, and also Ami Fikri. Okay, so we go to introduction. Okay, firstly, torsion test allows direct measurement of the shear modulus, which is G, of a material. This ability makes torsion testing, although not as common, a useful partner or tensile testing in determining the mechanical properties of a material. There are two kinds of torsion experiments, which is torque control and angular speed control. Torque control experiments apply a uniformly increasing torque to the specimen, and the amount of strain is measured as an angle through which the specimen has turned. Angular speed control turns the specimen at a specific angular speed while the torque is measured. Next is angular speed control is the type of experiment we will be doing. Thus, the directly measured quantity in this experiment will be torque. Young modulus, which is E, is related to the shear modulus, and finding E with the experimentally obtained G reinforces this relationship. They are dependent upon one another according to the equation G equals to E divided by 2 bracket 1 plus V, whereas V is a Poisson's ratio. Okay, next we go to theory. Okay, firstly, when a circular shaft is twisted at either end with no other forces active upon it, the bar is said to be pure torsion. If we let the left hand end of the shaft remain fixed, then the right hand and the bar will rotate through an angle with respect to the left end, and we will see the figure 1.1. And simultaneously, a longitudinal line on the surface of the bar, such as line and end, will rotate through a small angle with respect to the position and end. Because of this rotation, a rectangular element on the surface of the bar, such as the element shown in the figure, between two cross-section distance dx part, is distorted. This element is shown again in figure 1.2, isolated from the remainder of the bar. Okay, this is figure 1.2, which is element ABCD of torsional bar. During torsion, the right hand cross section of the original configuration of the element ABDC rotates with respect to the opposite face, and points B and D move to B and D respectively. The length of the sides of the element do not change during this rotation, but the angles at the corners are no longer 90 degrees. Thus, the element is undergoing pure shear, and the magnitude of the shear strain is equal to the decrease in the angle BAC. Okay, next is the distance BP is the length of a small arc of radius r subtended by the angle, which is the angle of rotation of one cross-section with respect to the other. Thus, BB equals to r. Also, the distance AB is equal to the length of the element of S. Okay, next is under pure torsion, the rate of change S of the angle of twist are constant along the length of the bar. This constant is equal to the angle of twist per unit length. Thus, where L is the length of the shaft. Okay, now we can see the figure 1.2, which is shear stress in torsional bar. Now observe that for linear elastical material, the figure of the shear stress that is shown in figure 1.1. From here, we can establish the relationship between the applied torque T and the angle of twist which it produces. The resultant of the shear stresses shown in figure 1.3 must be statically equivalent to the total torque T. The shear force acting on an element of area dA, shown shaded in the figure, is dA. The total torque T is the summation over the entire cross-sectional area of these elemental moments, where J is equal to the polar moment of inertia and the circular cross-section. Thus, we have theta equals to T over Gj. Okay, note that GJ is called the torsional rigidity of the shaft. Finally, since the total angle of twist is equal to L, and this is the result we want. The experiment we are about to perform will yield data on the torque T and the angle from which we can calculate G, the shear modulus given the dimensions of the shaft. Important to note that for a solid circular shaft of uniform radius. Okay, this is the formula. J equals to pi r4 divided by 2, and it also equals to pi d4 equals to divided by 32. Okay, thank you.
Assalamualaikum. My name is Ledin, and I'll be talking about the procedure. The first thing we should do is the specimen length and diameter are recorded and measured at 3 different points, and the average length and diameter are calculated. The pulley length is also measured. The readings are all recorded into table 1.1. The specimen is then mounted in the testing machine, and then the specimen is tested. Make sure the pulley is at a horizontal position. The third thing to do is the angle indicator is then attached and the readings are zeroed. The angle of twist when the load is added from 0 Newton to 200 Newton, and when the load is removed from 200 Newton to 0 Newton for both specimens are measured. The readings are recorded in table 1.2 and table 1.3 respectively. We continue with the observation. When measuring the diameter of the specimen, ensure that the equipment or apparatus used to measure the specimen has been properly calibrated to prevent any error from occurring. When taking the angle readings, ensure that the eye level of the person taking the reading is perpendicular to the reading to avoid any parallax error from occurring. Lastly, it is important to slowly apply the load so that it does not affect the results that we want to obtain from this experiment. Thank you.
We will continue with calculation. First, best specimen torsion constant equal to pi times d power of 4 over 32. The answer is 1.55 times 10 power of negative 10 meter power of 4. Theta equal to 14 degrees over 180 degrees times pi equal to 0.2443 rad. Shear modulus G equal to T times L over J times theta. The answer is 32.9 gigapascal. G equal to E over 2 times 1 plus V. The answer is 25.42 gigapascal. For shear stress, TR over J. The answer is 39.83 Pascal. And the last one, shear strain equal to shear stress over G, which is the answer is 9.087 times 10 power of negative 10. For mild steel specimen, torsion constant equal to pi d power of 4 over 32. The answer is 1.498 times 10 power of negative 10 meter power of 4. Theta equal to 7 degrees over 180 degrees times pi equal to 0.1222 rad. Shear modulus G equal to TL over theta J. The answer is 65.31 terapascal. G equal to E over 2 times 1 plus V. The answer is 53.42 gigapascal. For shear stress TR over J, the answer is 315 kilopascal. And the final one, shear strain, shear stress over G, the answer is 4.82 times 10 power of negative 9.
Assalamualaikum warahmatullahi and salam sejahtera. My name is Muhammad Amir Fikri bin Muhammad Noor. My matrix number is CD180200 and I am from group 2. So we are doing torsion test as our lab report. I will present to you the discussion and conclusion. So in discussion we have a few questions. First, if the cross section of shaft is not cylinder, explain how to perform the torsion analysis. So to perform the torsion analysis on non-cylindrical shaft, warping in square cross section by using styrofoam as specimen of square cross section in which grids were drawn along the faces of the specimen, then twisting the specimen as shown in figure 2. So you can see A is we are using the styrofoam as our specimen, and we draw the cross section in grids, you can see, and then the B is the result of the twisting. Sorry, the next step is twisting. Next, the warping was proceeded by using membranes analogy, which steel plates with a square hole as well as a round hole were used. So the edges of the hole were steadily clamped with rubber sheets, and by applying the pressure beneath the plate made it bulge. So the result of the bulges you can see or torsion heels. You can see at the figure 2. Alright. And then this is figure 3, the torsion heel for square cross section. So however the square cross section for the square hole, the membranes will be forced to lie flat as a zero slope at the corners and a steeper slope at the midpoints of the outer edges. So we are made aware of the fact that the torsional shear stresses in a shaft of arbitrary cross section are proportional to the slopes of a suitably inflated flexible membrane, which is membrane analogy. So thus the stress is a maximum at the midpoint of the outer edges of a square shaft and not at the corners. So in the corners the membrane has a zero slope, indicating a zero stress. So next question is briefly explain some of the important factors in designing a high quality shaft. So the shaft should be such that the shaft design should have enough mechanical strength. So what do you mean by that? The strength should be such that it should withstand all loads without causing much residual strain. Number 2, the cost of material and its processing must be weighed against the need for smaller shaft diameters. So based on the material properties, it should have high strength, good machinability, low notch sensitivity factor, and a good heat treatment properties. Okay, and the last one, in designing shaft on the basis of strength, the following cases may be considered. First, shaft subjected to twisting moment only, and then bending moment. Third one is the combined twisting moment and bending moment, and the fourth one is the subjected to fluctuating load solid and hollow shaft. When the shaft is subjected to combined twisting moment at the bending moment, then the shaft must be designed on the basis of two moments simultaneously. So that's only for discussion. we're moving on to conclusion. So, based on the conclusion we have based on the lab experiment that we have performed, we have concluded that the torsion tests have been performed on two different materials, which brass and mild steel, and with the help of the experiment data, value of the modulus of rigidity and shear stresses is calculated. So mild steel has the maximum value of modulus rigidity and applied torque at failure, which means that mild steel is stronger material compared to brass as it withstands higher shear stress. Brass has least value of angular displacement at the fracture. It shows that it has the lowest ductility compared to mild steel. However, the problem we encountered during this experiment that it is impossible to predict the point where failure occurs as a result of torsioning of torsion loading. It mostly occurs at that point which has any internal defects or cracks. So as to improve the results, it is important to keep the diameter constant and vary the length of the material. It is to find the mean value so it is more accurate and the zero error is eliminated from from finding the actual value. So the torsion testing machine should be changed as it is old and less accurate. So that's it for our discussion and conclusion. Thank you.